Hello everyone, it's lecture 3, right? And it is basically dealing with the question and answers and that you have asked about lecture 2. Right, first of all, ligands, if you consider ligands, right? So we can categorize ligand on the basis of their charge into 3 ways: positive, negative, and neutral, right? In either situations, they could be positive, negative, or neutral. Every kind of a ligand will bring 2 electrons. It's mandatory that every ligand has to bring 2 electrons, even it is a neutral, negative, or a positive ligand. And second thing is about inner d and outer d electrons. When any metal use 3d orbital, that complex is called inner d complex. When any metal use 4d, then we call it as outer d complex, right? Because 3d is coming before 4d, so it means it's inner d, and same is true the outer d complexes, right? And now the next question is how many ligand can bring 2 electrons, and this is a constant rule, right? For coordinate compounds, we need to believe they should possess lone pair, right? And when they possess lone pair, so automatically pair means 2 electrons, right? So all of them will bring 2 electrons, right? So it's a constant rule for all the complexes for every single ligand. Okay, I believe it is more clear, but just for practice, I will give you some other examples. Like you can take the example, previously we have considered the ammonia as a ligand, which was the weak ligand. Right now, I'm making another complex with the strong ligand, right? If you just want to enlist the ligands like strong and weak ligands, there are few ligands, those are strong. In fact, cyanide is the only one that we will consider as a strong ligand, while fluorine is a weak ligand, chlorine is a weak ligand, water is a weak ligand, ammonia is a weak ligand, right? So all of these are weak ligands, and at the same time it is negative ligand. As you can see, this negative charge. Fluoride is a negative, chloride is a negative ligand, ammonia is a neutral ligand without any charge, and same is true with the water, it is also a neutral ligand. Okay, and now we can take the example of cobalt with hexacyano. Hexa means 6 and cyano means whenever we are writing about negative ligand like chlorine, normally when it is having negative charge we call it as a chloride, right? Chlorine to chloride, right? But when we talking about as in ligand form in a coordination complexes, it's become chlorido, right? It's like cyanide to cyano, right? So it's hexacyano with cobalt complex. Okay, what you need to do, step 1 is to consider the electronic configuration. Cobalt belongs to which system? Like previously we have considered, like it belongs to D7 system. Okay, yes, one more thing to share. Okay, let me complete it first. D7, 3D7, 4s2, 1 2 3 4, it's 7 electrons, it's 2 electrons, right? Okay, because if you consider the negative oxidation, so oxidation state of cobalt, It is having overall -3 charge. Cyano is a negative ligand, so one cyano is having -1 charge. Now we have 6, so it's become -6, right? So -6 -3. How you will get -3? So it means the metal should have +3 charge. Okay, so you need to remove 3 electrons from this, right? 2 from 4s2, right? They just gone, and 1 from 3d7 to 3d6, right, from d orbital. Okay, you have to rewrite it. I'm just erasing it. 1 2 3 4. So we are left with 6 electrons. Okay, you see, you need to accommodate the 6 ligands. To accommodate the 6 ligands, you need 6 empty orbitals. Okay, so we need 6 places because cyano is a strong ligand, and the strong ligand has ability to pair up the electrons, right? So what will happen when the cyano approaches? So it pull the electrons, no, sorry, it pushes the electron to become pair up. Previously we have 6, still we have 6, but with 2 empty spaces. you know it's a cyano cyano will occupy the d places, 3d, right? Then we need 6 places. After 3d we need to fill a 4s. After 4s we need to consider 4p, right? So 1 2 3 4 5 6 we have done with the 6 places. Cyano, 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 cyano. So every time cyano is coming up. Okay, so 1 2 3 4 5 and 6 places. Just check how many orbitals of d. It's 3d, it's 4s, it's 4p, right? So we are using the ligand is using 2 orbitals of d, so it's d2, then 1 of s, and 3 of p, d2sp3. Once again it goes to octahedral geometry, right? Okay. Next thing to consider is the spin quantum. You see, all the electrons of like this was the previous state, right? So all the electrons of metal are paired. If you just calculate the spin, plus half, minus half, 0, plus half, minus half, 0, plus half, minus half, 0, so its value is 0. The spin quantum number is 0, right? So it's a low spin complex. In the previous lecture that was a high spin complex, right? So the complex could be low spin, high spin, inner d, outer d. Okay, so what do you say? Is it a inner d or outer d? Because it is using 3d, the d orbital. You need to consider the specifically d orbital. If somebody is using inner d, right, then it's inner d complex. If ligands are filled up in the outer d, then it's become outer d complex, right? So it's 3d, 4s, 4p. So there is no utilization of 4d, so it's not outer d complex, it's a inner d complex. And the geometry is octahedral, and hybridization is d2sp3, and spin quantum number is 0. That's it. Thank you.